Hello friends, welcome to engineering tutorial. So we'll continue our discussion related to AC circuits. Previously we discussed AC circuit with pure resistance, with only resistance connected. In this video we are going to discuss about AC circuit with pure inductance. Previously we discussed pure resistance. Here we'll discuss pure inductance. So let us say we have a circuit. We have an inductor of inductance or self-inductance L. We have an alternating voltage Vt connected to it. This will result in the flow of an alternating current. Now, in AC circuit with pure resistance, the driving force, behind the current flow in the circuit, it was based on Ohm's law. Okay, I is equal to V by R or V is equal to IR, that. But here, the explanation for the current flowing in the circuit because of the applied voltage, it is given as per Faraday's law. Faraday's law of electromagnetic induction. Okay, and also Lenz's law. But here we're going to ignore the sign. So we are only going to focus on the magnitude. Okay, here. So when an alternating voltage is applied to a pure coil, inductive coil of self-inductance L, a EMF is induced in the circuit because of the rate of change of current, rate of flow of current through the circuit. This situation is given by Vt is equal to L dit by dt. Actually, Vt is directly proportional to the rate of change of current. So here Vt is the voltage across the inductor. If we apply KVL here, it will be Vt minus VLT is equal to 0. That implies Vt is equal to VLT. So whether you write VLT or Vt, it is the same thing. Okay, so this is equal to this. Vt is equal to L dit by dt. Now Vt can be expressed in the form of sinusoidal expression, which is given Vmax sin omega t. Okay, so we'll substitute the same here. That implies Vmax sin omega t is equal to L dit by dt. Okay, the current is time varying, the voltage is time varying, so derivative of the rate of flow of current with respect to the time. Now here our objective is to find the expression of current. So what we'll do, we'll write L dit is equal to Vmax sin omega t dt. That implies dit is equal to Vmax sin omega t, Vmax by L sin omega t dt. Okay, yes. Now in order to get the expression of current, we'll integrate both sides. Okay, integrating both sides with respect to t. dit is equal to Vmax by L, as it is constant, it will go outside the integration sign and it will be sin omega t dt. Okay, this. So now this becomes, that implies it is equal to Vmax by omega L. Here we are integrating it with respect to t. So omega, angular frequency, behaves as a constant. So Vmax by omega L, integration of sine, is minus cos omega t. So we can write this as minus cos omega t, as that implies it is equal to Vmax by omega L sin omega t minus pi by 2. We can write sin omega t minus pi by 2 in place of minus cos omega t. Why? To bring both the voltage and current into the same format, sine format. So this is the voltage, the expression of current, and the expression of voltage is Vt is equal to Vmax sin omega t. Now we can write this it as Imax sin omega t minus pi by 2, where Imax is equal to Vmax by omega L. Okay. Now here there is something very interesting. This omega L part, this is called as inductive reactance. It is expressed as X subscript L, inductive reactance. It has units in ohms. Okay, XL is equal to omega L, which is also equal to 2 pi FL. Also, an interesting thing is that inductance and capacitance, the reactance of inductor and capacitor, they are expressed in terms of imaginary numbers. So here actually this XL is plus j omega L. Okay, plus j omega L, where j is the iota root over of minus 1. Okay, root over of minus 1. We are going into the domain of complex numbers. So inductance and capacitance, when I will discuss capacitance, I will tell you what is the expression of capacitive reactance in terms of imaginary numbers. But here you just remember that inductive reactance is expressed as this, j omega L. Capacitance and inductance, they have imaginary number associated with it, j. But resistance is real in nature. Resistance is real. Okay, so this is expressed as the inductive reactance XL is omega L in terms of complex numbers, complex notation, that is plus j omega L. So this is the expression. So from these two expressions, what do we understand? What do we get? It means that current lags behind voltage by pi by 2 radian or 90 degree. This current lags behind voltage by pi by 2 radian or 90 degree, or we can say voltage leads current by pi by 2 radian or 90 degree. Okay, this is the thing. So here if we have to express it in terms of waveforms, it will be something like this. So this is the circuit of AC circuit with pure inductance, like we did. So the waveform is something like this. As you can see here, the waveform in black, the sinusoidal AC waveform in black, it represents voltage. Okay, it starts from 0, the 0 point, the starting 0 point, and then it completes one full cycle. If you see the starting 0 point of current waveform in red, it starts from here at pi by 2. It means it lags behind the voltage by a margin of pi by 2. Okay, pi by 2. The corresponding 0 points they differ by pi by 2. Also, their corresponding positive peaks, their corresponding negative peaks, and the final 0 point, they all vary by pi by 2. Everything, there is a difference of pi by 2 radian or 90 degree. This is the waveform, the AC waveform for voltage and current. The current lags behind voltage by 90 degree or pi by 2 radian, or voltage leads current by pi by 2 radian or 90 degree. In whichever way you want to express it, it will be correct. This is the waveforms. Now suppose we have to draw the phasor diagram. So it will be something like this. So what I told you, voltage leads current by pi by 2 radian or 90 degree, that's one way of expressing it. Or current lags behind the voltage by pi by 2 radian or 90 degree. So this first phasor diagram, it is drawn with IRMS, or the current, RMS value of current, as reference. Now as I told you, it is a common practice to draw phasor diagrams with RMS values of current and voltage. So here IRMS is taken as reference, that is parallel to the positive x-axis. Okay, so here voltage leads current by pi by 2 radian or 90 degree. So this 90 degree or pi by 2 radian. This voltage leads current. This. Okay. Now if we change the situation, we go the second way, where we take VRMS, or the RMS value of the applied voltage, as reference axis. Okay, reference phasor. So that is taken parallel to the positive x-axis. So here what is said, that current lags behind the voltage by pi by 2 radian or 90 degree. Okay, pi by 2 radian or 90 degree. So it is at the bottom in this way, like this. It lags behind the voltage by pi by 2 radian or 90 degree. Okay, here voltage leads current by pi by 2 radian 90 degree. Here current lags behind voltage by pi by 2 radian or 90 degree. This is VT leads IT. Here IT lags behind Vt, all by a margin of pi by 2 radian 90 degrees. So whichever way we want to express it, it will be the same thing. If we just rotate this diagram, if we rotate this diagram like this, we'll get the same result. Let me show you. Okay, so if we just rotate it to the right like this, it will get the same diagram. It's the same thing. Okay, both the diagrams, they are the same thing, just it's a different way of representing. Okay, let's take it back to the original. Okay, this. So this is the thing that you have to understand. This different ways of expressing the same thing. Okay, now another thing which you want to understand here, you can also understand why current and voltage, they have respective phase differences. We just got to know that inductive reactance is written as plus j omega L. Okay, so let us say we have this circuit. The applied voltage is Vt. This is the inductor with self inductance L, and with inductive reactance XL is equal to plus j omega L. Now the voltage drop across the inductor is given by I into plus j omega L. Now if we apply KVL, we got to know that Vt is equal to VLT as per Kirchhoff's voltage law, applying KVL in the closed loop. So Vt is equal to plus j it omega L. Okay, so we know that if we draw the complex number axis, okay, here like this, this is the positive real axis, this is the negative real axis, this is the positive imaginary axis or plus j axis, this is the negative imaginary axis or minus j axis. So here Vt is plus j it omega L. So whatever it is, the voltage, it is plus j, so it lies on this axis here. This is Vt. Okay, this. And VLT and IT, if we take that, it is in the, it has no imaginary part and it is positive. So this is IT. This is IT, this is Vt. So voltage leads current by pi by 2 radian or 90 degree, or current lags behind the voltage by pi by 2 radian or 90 degree. So if you go by the complex number approach as well, complex axis, positive and negative, real and imaginary axis as well, you will get the same result. Okay, okay, now there is another thing, which is the power absorbed in the circuit. Okay, instantaneous power. First, the heading is power absorbed in the circuit by the inductor. So first is instantaneous power. That is equal to product of the instantaneous voltage and current. Okay, Vt into IT. Now here Vt is equal to Vmax sine omega t, and IT is equal to Imax sine omega t minus pi by 2, or we can write it as this, the original format which we got, which is minus Imax cos omega t. This, we'll use this expression. So it will be equal to, the instantaneous power will be equal to Vmax sine omega t into minus Imax cos omega t, which is equal to minus Vmax Imax sin omega t cos omega t. So here what we'll do, it will be equal to minus Vmax Imax by 2, and here we'll multiply 2 as well, 2 sin omega t cos omega t. We divided and multiplied 2. So here we get minus Vmax Imax by 2 sin 2 omega t. So we know sin 2x is equal to 2 sin x into cos x. We have used that identity. Now sorry, next is, this is the instantaneous power. Okay, this is the instantaneous power. Now we have to find out the average power over one cycle. Now the average power P average is equal to 1 by T 0 to T instantaneous power Pt dt over one complete cycle, over the entire time period. So this is equal to 1 by T 0 to T minus Vmax Imax by 2 sin 2 omega t, which is equal to minus Vmax Imax by 2t 0 to t, this is sin 2 omega t dt, sin 2 omega t dt. So this is equal to minus Vmax Imax by 2t into 1 by 2 omega, and this will be minus cos 2 omega t, minus cos 2 omega t and 0, because 2 omega behaves as a constant here. We are integrating with respect to t. So 1 by 2 omega minus cos 2 omega t 0. Now this becomes minus Vmax Imax by 4 omega t, and this minus will go outside and become plus. So this will be cos 2 omega t minus cos 0. Now we know that omega is equal to 2 pi by t, which is equal to 2 pi f. That implies omega t is equal to 2 pi, where capital T is the time period. So this becomes cos 2 omega t becomes cos 4 pi. So cos 4 pi minus cos 0, which is equal to 1 minus 1, 1 minus 1, that is equal to 0. So this entire thing becomes 0. So the whole result is 0. So the average power over one complete cycle in a circuit with pure inductor, that is equal to 0. Yes, the average power is 0. Now suppose we want the instantaneous power curve waveform. Okay, so in that case this is the instantaneous power curve. So pay attention, this is the waveform of voltage and current, instantaneous voltage and current. Here the blue one, it represents the power curve. So pay attention, okay, here see, from, let me use a different ink here, okay, from 0 to pi by 2, from 0 to pi by 2 radian or 90 degree, here voltage is positive, voltage is in this axis, the positive axis, top axis. So voltage is positive, okay, voltage is positive, but the current, the red curve, that is in the negative axis, downward axis. So it has negative value, current has negative value. So the power curve, which is the product of voltage and current, it will be positive into negative, which is negative. Okay, here this is the magnitude downwards, the blue curve, but it is in the negative direction. Okay, so that's why the power curve from 0 to pi by 2, that is negative in the downward direction. Then from pi by 2 to pi, okay, let me write here also so that there is no confusion. This is positive, this is negative, that's why product of positive and negative, that is negative. From pi by 2 to pi, okay, pi by 2 to pi, voltage, this much portion, from pi by 2 to pi, this much portion, the black portion, voltage is positive, current, the red portion, that is also positive. So power is product of voltage and current, that is positive into positive, which is positive. That's why it has a positive peak here. See, from pi by 2 to pi, this red one, that is positive, the black one, voltage, that is also positive, product of positive and positive, the power curve is also positive from pi by 2 to pi. Next, from pi to 3 pi by 2, okay, from pi to 3 pi by 2. See here, voltage, this black one, it is in the negative direction, downward direction. So voltage is negative, current, the red one, it is positive, current is positive. So power will be negative into positive, that is equal to negative. So that's why from pi to 3 pi by 2, the power curve is in the downward direction, negative. Magnitude wise it is the same in both upward and downward direction, but depending upon the sign or the direction of the curve of the voltage and current waveforms, the direction or sign of the power curve is changing. Then from 3 pi by 2 to 3 pi by 2 to pi, here voltage is negative, current is negative. Okay, from 3 pi by 2 to 2 pi, voltage is negative. Okay, here voltage is negative and current is also negative. Current is also negative. So power is negative into negative, that is equal to positive. So that's why from 3 pi by 2 to 2 pi, where current is negative, sorry, here not this one, not this one, this much portion. This portion, this is positive, negative, and this is also negative. So that's why negative into negative, this is positive in nature. Here current is positive, from pi to 3 by 2, current is positive, voltage is negative. That's why positive into negative, here it is negative. Okay, so this is the power curve, and obviously you will find the peaks of the power curve, they are higher than the respective peaks of voltage and current, obviously, because it is the product of both the values, voltage and current. So obviously it will be, the peaks will be higher and the negative peaks will also be higher in the downward direction. Both upward and downward directions, the positive and negative peaks are higher than the respective positive and negative peaks of voltage and current. Okay, but depending upon the sign of the voltage and current waveforms, in which direction, whether they're in the upward direction or downward direction, the direction of the power curves, they vary. Okay, so here I have shown it. So this is the study of AC circuits with pure inductance. Okay.